Welcome to classes by Inspire Physics. Today we are going to see an application of Gauss's law. Using Gauss's law, we need to find the electric field due to an infinite size thin sheet of charge. Okay, so we have a thin sheet of charge of infinite size. See, this is a thin sheet of charge. It is having infinite size. The sheet is containing large number of positive charges. And it is having infinite size, so we don't know about the total charge, but we know about the charge density. Sigma is called charge density. What is charge density? Charge per surface area is called charge density. Okay, now due to symmetry, this thin sheet of charge, for example, if this is a sheet of charge, this sheet of charge will produce electric field perpendicular to it on either side. If it is containing charge, this charge can produce field in this direction as well as in this direction. See, on either side it will produce a field in perpendicular direction. Okay, so here we can see the sheet is producing field in this direction as well as in the backward direction. In both sides it will produce electric field of same strength. Now what our aim is, we need to find electric field at a particular point here. Okay, so at this point what we will do, we will consider a small a shape, a circular shape like this. Now through this area there will be electric flux passing. Now let electric field at this point be directed in this direction. Now we need a closed surface. If we need to apply Gauss's law, we need a closed surface. So through this area, value of the area is a dA, and the area vector is acting in the same direction, vector dA. This is the area vector along the direction of electric field. Through this flat face, circular face, there will be electric flux passing. Okay. Now what we will do, we need a closed surface. To make a closed surface, we imagine another circular shape like this, circular area like this, having same area. Then this is also having area vector in the same direction dA. This sheet will produce electric field on the other side. So this side also has electric field. I can say this is the direction electric field. E is the direction electric field. Now we have got two flat faces, circular faces. Now I will make this a cylinder. Imagine a cylinder passing through it. So this is a curved face of the cylinder. It is imagined to be passing through it. This is a cylinder. Through these two flat faces there is electric flux passing. But through the curved face there is no electric flux passing, because through the curved face, if you just take a small area on the curved face, this is the area vector. I can say dA vector dA, and electric field is along this direction. I can say this is a direction electric field. See, this is a direction electric field. What is the angle between them? The angle is 90 degree. So there is only electric flux passing through these two flat faces. Okay, through flat face only there is electric flux passing. Now we need to write equation for the flux through each face. See, on the right face, I can say flux through the right face phi r is equal to d phi r. Small flux through this face is equal to, what I can say, we can take this E dot dA. E dot dA, but E and dA are in same direction. So what we will take? We will take E into dA, because same direction means angle is 0, cos 0. So E into dA. Then on the left face we can say d phi L. That also having same equation, E into dA. Okay. Now what is the total flux? Total flux through these two faces. We need to add these two. See, total flux we need to add d phi R plus d phi L. We need to add. What's the total flux through these two faces? It will be equal to, when you add these two, you will get 2E into dA. dA is the area of this circular face. Here also having same area, it is also dA. Now according to Gauss's law, the total flux through the curved or the cylindrical Gaussian surface will be equal to, it is equal to 1 by epsilon 0 times net charge enclosed by the Gaussian surface. See, this is a circular area corresponding to an area having a same area value dA. See, in this region there is charges enclosed. We need to consider only those charges within this area. See, if sigma is charge density in an area dA, how many charges will be there? Sigma into dA. This is the charge enclosed. So 1 by epsilon 0 times sigma into dA is a charge enclosed by the Gaussian cylinder. Okay. Now comparing these two, left side is 2E dA, right side is 1 by epsilon 0 times sigma dA. dA cancels, and what is the electric field is equal to sigma by 2 epsilon 0. Okay, this is the expression for electric field. This electric field is acting in this direction. Okay, this is a direction of electric field. In this direction, we can imagine a unit vector r cap. So we can say in vector form, vector E is equal to sigma by 2 epsilon 0 r cap. This is the vector form of the electric field due to a thin, infinite size thin sheet of charge. Okay, we have got the equation. Now we need to plot a graph. We need to see the variation of electric field with a distance. See, R is taken along x-axis, electric field along y-axis. See, we know that the electric field in the equation, there is no term relating the distance. So we can say, whatever may be the distance, the electric field is having a constant value. Electric field is it is constant. At each and every point, if you move far away from the thin sheet, the electric field will be constant. So we will get a horizontal line. Okay. Now we have another application. Means we have only one sheet. We have got equation electric field. Now what will happen if you have two sheets like this? See, we have two sheets. So one sheet, one parallel sheet. Okay, we have one more parallel sheet. Both parallel sheets are having charges. Suppose both are having positive charge, but they have different charge density. Here we can say sigma A and this is sigma B. We just divide the region into three. First region, second region and third region. See, we will find the electric field in these three regions. Okay. Now at this region, region 1, I select a point here. At this point, this positive charge will produce a field. Okay. It is away from the charge, away from the sheet. This sheet also can produce a field here in the same direction. I can say this also in the same direction. What is the field due to first sheet? I can write first sheet will produce a field sigma A by 2 epsilon 0. This sheet also produces the same field, that is sigma B by 2 epsilon 0. Two fields are in the same direction. What's the net field? We need to add them. So I can say in the region 1, the net field is equal to 1 by 2 epsilon 0 is common. What is the field? Sigma A plus sigma B. Okay. Since this net field is towards left side, to indicate a direction, if you want, we can put a negative sign also. Minus 1 by 2 epsilon 0 sigma A plus sigma B. Now in region 3, I just choose one point. This positive charge sheet will produce a field in the rightward direction. This also will produce a field in the same direction. Okay. What about the net field in region 3? As we have seen here, both fields are towards the right side. Both having the values like this field is having a value sigma A by 2 epsilon 0. This also having a value sigma B by 2 epsilon 0. So both are in same direction, we need to add. So in region 3, we have the equation 1 by 2 epsilon 0 is common. Sigma A plus sigma B. This is the net field. Okay, in region 1 and region 3. Now come to this region, region 2. See, if you consider a point here. This charge, this sheet, charged sheet will produce a field away from the sheet. This is the direction. This will produce a field also away from the sheet. This will be the direction. Okay. So this sheet produces a field having a value sigma A by 2 epsilon 0. This produces a field sigma B by 2 epsilon 0. What is a net field? See, we need to subtract because they are in opposite direction. What's the net field in second region? It is sigma A by 2 epsilon 0 minus sigma B by 2 epsilon 0. Because they are in opposite direction, we will get 1 by 2 epsilon 0 sigma A minus sigma B. This is the situation. Okay. So in the three region 1, region 2 and region 3, we have got the different values of electric. Here in these two regions, magnitude of the electric field is same. But here we put a negative sign to show that net field is towards the left side. This was to the right side, we have taken positive. Left side, we have taken a negative sign. Means according to sign convention. Here, both fields are in opposite direction, so we have subtracted to get the net field. Now similar to this, we have one more situation. See, here we had both sheets are having same charge, positive charge, different charge density. Suppose we have the sheets like this. We have one sheet. It is positively charged with a charge density plus sigma. See the other sheet. It is kept parallel to first sheet. It is charged with a negative charge, same charge density, we can say minus sigma. Now we take 3 points. Region 1 we have, region 2 and region 3. 3 regions we have. We choose a point here. In region 1, this sheet, since it is positively charged, it will produce a field away from it. Okay, we know the direction of field. What is the value of this field? Sigma by 2 epsilon 0. Okay, now this sheet, it is negative charge, so it will produce field towards the sheet. This is the direction of the field. What's the value of the field? Again, same charge density, so sigma by 2 epsilon 0. See, both vectors are in opposite direction. What's the net field? In region 1, we need to subtract sigma by 2 epsilon 0 minus sigma by 2 epsilon 0. We will get a value 0. The net field will be 0. See the region 3. In region 3, when we consider, see if you have a point here, negative charged sheet will produce a field. The negative charge is producing a field towards a charge. Okay, this is towards a charge. This is a field. What's the value? Same value, sigma by 2 epsilon. This positive charge sheet will produce a field away from the charge. See, in that direction, this is a field that also sigma by 2 epsilon. Again, both vectors are in opposite direction, same magnitude. What's the field? As we have seen here, sigma by 2 epsilon 0 minus sigma by 2 epsilon 0, net field will be 0. Now come back to this point, region 2. The positive charge sheet will produce a field in this direction. Negative charge sheet will produce a field away from the sheet. See, both are having, so what we can say, the negative charge sheet will produce a field, see, the negative charge sheet will produce a field towards a charge. Positive charge sheet will produce a field in the, away from the charge. Okay, so this will be the direction. This charge, the sheet will produce a field towards the sheet. This is away from the sheet. So both the fields are in same direction. So which are the field values? For this we have sigma by 2 epsilon 0. This also we have sigma by 2 epsilon 0. Two sheets in same direction. Two field in same direction. So what's the net field? In region 2 we have sigma by 2 epsilon 0 plus sigma by 2 epsilon 0. Because two field in same direction, what's the value? 1 by 2 epsilon 0. We will add sigma plus sigma 2 sigma. 2 cancel, you will get sigma by epsilon 0. This is the net field. Okay, this is the net field and the region between these two sheets. Okay, so we have seen an application of Gauss's law, and along with we have seen two different situations. Having two sheets, thin sheets kept parallel to each other. In first situation, we have two sheets of same charge but different charge density. Here opposite charge but same charge density. We have got 3 results. For this situation, we have got 3 results. Here also we have got 3 results for 3 different regions. Okay, I hope that you have understood. Thank you.